Hello everyone, my name is Manu Shukla and I am a third year student at IIT Guwahati in the BSc Honours Data Science and AI program. This is my term project 3 for the ninth trimester. I have built a movie recommendation system using cosine similarity. Now I will walk you through the code base, the results and the conclusion based upon that. Defining the problem statement. The core problem this project solves is choice paralysis in the era of digital streaming. Today, platforms offer tens of thousands of titles, meaning users frequently spend more time endlessly scrolling and searching for a movie than than they do actually watching one. Without a system to filter this massive amount of data, the user experience completely breaks down. This is critical real-world business challenge. If a user cannot find relevant content quickly, they get frustrated and cancel their subscription. To tackle this, I built an automated recommendation engine that relies purely on the item's metadata. By analyzing the actual DNA of a movie, its plot overview, genres, and keywords, this system instantly calculates and recommends the top 5 most similar films, keeping the user engaged and solving the problem of information overload. Now I'll be explaining the tools and dataset. For the foundation of this project, I used Python due to its incredibly powerful data processing ecosystem. I relied heavily on pandas to load, clean, and manipulate the data. Our dataset is sourced from TMDB, and as you can see here, I used pandas to strip away the noise and isolate just the 5 critical columns we need: the movie's ID, title, overview, genres, and keywords. This is the line. To build the actual recommendation engine, I utilized scikit-learn. Instead of building complex math from scratch, scikit-learn provided the count vectorizer to efficiently translate our text data into numerical matrices, and the cosine similarity function to calculate the exact distance between those movies vectors to find the perfect match for the movie. Let's move to the code base now. Highlighting this line, our first key decision was feature engineering, specifically creating a unified tags column. Instead of analyzing plot overviews, genres, and keywords in isolation, I converted all text to lowercase and merged them into a single string per movie. This bag of words approach ensures that every descriptive aspect of a film is evaluated as one consolidated textual profile. The next step, the next step was using count vectorizer. Max features equals to 5000 and stop words equals to English. I used scikit-learn's count vectorization. I explicitly set stop words equals to English, which automatically removes common filler words like the, is, which are just the grammar. By limiting max features to the top 5000 words, we keep our metrics computationally efficient and prevent rare noise from cluttering our vector space. The next step was to use cosine similarity. With our text represented as numerical vectors, I computed the cosine similarity matrix. We choose cosine similarity over distance-based metrics because it measures the direction of vectors rather than the magnitude, meaning short overviews and long overviews can still be matched accurately based purely on content alignment. This generates a dense lookup matrix containing similarity scores between 0 and 1 for every pair. If the score is between 0, if the score is close to 0, then the movies are not matching. If the score is close to 1, then the movies match perfectly. This is the final recommendation function logic. Inside our recommend function, we locate the input movies index, pull its corresponding similarity row, and sort the scores in descending order. This is the line that does the task. By using enumerate, we preserve the original row indices during sorting. We then slice from 1 to 6, which cleanly skips index 0, the movie matched with itself, and instantly returns the top 5 closest recommendations. To start evaluating our results, let's examine the raw mathematical output generated by our vectorizer and cosine similarity engine, vec- vector matrix shape, and similarity matrix. As you can see on screen, our matrix output shows a shape of 4800 by 5000. This means each of our 4800 movies is now mapped as a distinct 5000 dimensional numerical vector. This is the similarity matrix. When we examine the row, when we examine each row in the similarity matrix, every calculated value sits strictly between 0 and 1. A score approaching 1 indicates highly overlapping tag directions, while a score near 0 means two movies share virtually zero keywords or genres in common. Next, let's run a qualitative sanity check in Python to interpret whether these mathematical weights produce logically sound recommendations or not. For testing, we have an input for the Dark Knight movie. When we pass an input like the Dark Knight, the algorithm outputs the Dark Knight Rises and Batman Forever, which are very close. Notice how the top recommendations have similarity scores hovering around 0.4 to 0.6. In text-based cosine similarity, a score above 0.3 represents significant structural overlap. The model correctly prioritized other Batman films and gritty action features because they share overlapping tags like DC Comics, Vigilante, Action, etc. Now, let's transition to the core output of this project, our live Streamlit web application. I built this interactive user interface to turn our backend machine learning logic into an intuitive product experience. When I select a high concept film like The Amazing Spider-Man and I click on recommend, the recommended movies are Spider-Man, Spider-Man 3, the Lego movies, etc. The application grabs the selected title, looks up its index, and retrieves its row from our similarity matrix in real time. The UI layout makes it easy for any user to quickly discover relevant movies. To test the system's flexibility, let's try an entirely different genre. Now we will input Toy Story. When we input an animated family movie like Toy Story, the algorithm shifts vector space entirely towards the Toy Story genre. I click on recommend, and the recommended movies are Toy Story 2, Toy Story 3 as the first and second recommended movies. Because our heavy matrix multiplication is pre-calculated during the pipeline setup, inferencing inside Streamlit takes less than 50 milliseconds. Furthermore, this highlights the primary advantage of content-based filtering. Even if a new movie has zero user ratings or viewing history, as long as we have its metadata tags, our application can accurately recommend it, completely overcoming the classic cold start problem. Now I'll be sharing the summary, the learnings, and the future scope. To wrap up this project successfully, we delivered an end-to-end content-based movie recommendation system by combining overviews, genres, and keywords into a consolidated tag representation, converting them into numerical vectors, and applying cosine similarity. The platform turns vast movie catalogs into instant top 5 personalized suggestions. My biggest technical takeaway was mastering vector-based text retrieval. I learned that why cosine similarity outperforms standard Euclidean distance for NLP tasks because measuring the directional angle of feature vectors allows us to accurately evaluate content alignment regardless of text length. For future scope, we could involve this into a hybrid system by adding collaborative filtering using live user ratings. We can also integrate the TMDB Live APIs to automatically fetch real-time movie poster thumbnails and migrate vector indexing to a cloud database. That's it. Thank you from my side.